Projectiles, inclined plane, type 2, vertical landing. So here we're given a question where we're told that the particle is projected up an inclined plane with an initial speed u, and the line of projection makes an angle alpha with the plane, which is itself inclined at an angle of beta with the horizontal. So if we were to sketch that, we have our inclined plane is at an angle of beta, and we have initial velocity of u, and it is inclined, it's projected at an angle of alpha to the plane. And then we're also told that the particle strikes the plane at right angles. So that means on landing, it is landing at 90 degrees. So that's the landing velocity there. Okay, so we know, and we have to remember that on landing, Sy equals 0 because the distance above the plane from the start and the finish is 0. So it's not landing below the plane, it's not landing above the plane, it's landing in the same distance above the plane as it started. But also because it's landing at 90 degrees, we know that there is no velocity in the x direction because it's literally coming straight down. So if it's coming straight down, it only has velocity in the y direction. So we now have two pieces of information that's going to help us prove this identity that tan alpha times tan beta is equal to a half. Now, there is no way you could look at that and see how am I going to prove tan alpha tan beta is equal to a half. Instead, you focus on this information here, what you know about when it's landing. So I'm going to get you to pause the video and you're going to fill out your table for U, A, V, S and T in terms of X and Y. Okay, so if you filled in your table correctly, we should have U cos alpha in the X direction, U sine alpha in the Y direction. We know our velocity has to be resolved in the X direction, so we saw that in the last example last week. So we have minus G sine beta and minus G cos beta in the Y direction. So you should always notice that it's cos sine alpha beta, sine cos alpha beta in your X and Y for your U and your A. So then if we're looking at V is equal to U plus AT, well then V in the X direction is U cos alpha minus G sine beta T, and V in the Y direction is U sine alpha minus G cos beta T. And then if S is equal to UT plus a half AT squared, then S in the Y direction is U cos alpha T minus a half G sine beta T squared. And S in the Y direction is U sine alpha T minus a half G cos beta T squared. And our time is in terms of T. Okay, so we're trying to prove this tan alpha tan beta equals a half. So we're going to take our two equations there. Vx is equal to 0 on landing and Sy is equal to 0 on landing. And what you can do is you can work out your time of flight for the first one and sub it into the second. Or what I like to do is I like to work out the time of flight for both and equate. So we're saying on landing, Vx is equal to 0. Why? Because it lands at right angles. Okay, so what did we say V of x was? We said V of x was equal to U cos alpha minus G sine beta T. So if I let that equal to 0, I can get the time of flight. So I get T is equal to U cos alpha divided by G sine beta. So in other words, I'm bringing G sine beta T on its own to one side and U cos alpha to the other side, and then dividing across by the coefficient of T, which is G sine beta. So So therefore that is my time of flight. So I'll call that equation 1. And then I also know that on landing, Sy is equal to 0. Okay, so what was Sy? Well, we said that Sy was equal to u sine alpha t minus a half g cos beta t squared. So if I let that equal to 0, I can factorise out my t as being common. I'm going to multiply everything across by 2 there as well to get rid of my fraction. And then I have my highest common factor is t. So that leaves me with 2u sine alpha minus g cos beta t is equal to 0. And then both of those should equal 0. So therefore again I can get t on its own here. So if I bring g cos beta t to one side and 2u sine alpha to the other side and divide across by the coefficient of t, I'll end up with 2u sine alpha over g cos beta. So now I have the second equation for the time of flight. Why do I get 2 t's? Well, this is at the start, the time is 0, and at the start the particle is sitting on the plane, so therefore there is no displacement above the plane in the y direction. So in other words, Sy is equal to 0 at the start and also at the end on landing, when the time is 2u sine alpha over g cos beta. So now I have 2 equations for the time of flight, so I'm going to equate these 2 equations. So we're going to say equate 1 and 2. So what was 1 and 2? Well, 1 was u cos alpha over g sine beta, and that's equal to 2u sine alpha over g cos beta. So now we have to do a little bit of trigonometry and a little bit of algebra. So I can see my u is gone on both sides if I divide both sides across by u. If I multiply both sides across by g, my g is also gone. And now what I can see is I have a lowest common denominator, which is sine beta cos beta. So you can either multiply across there by your lowest common denominator if you want, or you can think about what it is you want to be left with. So you want to be left with tan, and you have to remember that tan is sine over cos. So if I multiply, well, let's cross multiply, it's easier for you to see. Okay, so we'll go cos alpha cos beta is equal to sine alpha sine beta. Okay, and now what I want to do is divide both sides across by the, oh sorry, I have a 2 there as well, don't I? 2. So if I divide both sides across by my cos alpha cos beta, then I'm left with cos alpha cos beta over cos alpha cos beta is equal to 2 sine alpha sine beta over cos alpha cos beta. And of course cos goes into cos once, and sine over cos and sine over cos is equal to tan. So I'm left with 1 is equal to 2 tan alpha tan beta. And lo and behold, if I divide both sides across by 2, then I'm left with tan alpha tan beta is equal to a half, which is what we wanted to show. So we didn't focus on how were we going to get our tan alpha tan beta. Instead, what we focused on was what do we know about the landing, and we knew that the landing was Sy is equal to 0 and v of x is equal to 0. So that was the key to solving this problem. So we have a second part of the question here, which is telling us if beta is equal to 30 degrees, that we have to find tan alpha and also the time of flight in terms of u and g. So we go and we say, well, what do we know about tan alpha, tan beta? Well, we know tan alpha, tan beta equals a half because we've just shown that. So we're given that beta is equal to 30 degrees. So if beta is equal to 30 degrees and I sub that in, well, I get tan alpha, tan 30 equals a half. And if we go to page 13 in our maths tables, or else we use our calculator, making sure our calculator is in degrees, then that gives us that, which is 1 over root 3. So we have tan alpha times 1 over root 3 is equal to a half, and therefore tan alpha is equal to root 3 over 2. So if we just go dot, 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 tan 30 equals 1 over root 3. Okay, now if we go back, we're looking for our time of flight in terms of u and g. So I have 2 times the flight here. I can say u cos alpha over g sine beta, or I can do 2u sine alpha over g cos beta. So let's just go with the first one there, where t is equal to u cos alpha over g sine beta. So t is equal to u cos alpha over g sine beta. Okay, now that means that I can either work out what alpha is and I can work out what beta is by getting tan inverse in either case here, or I can draw my right angle triangles. So alpha is equal to the opposite over the adjacent, and with Pythagoras there, then if I get opposite squared plus adjacent squared square root, I'm left with root 7 here. In other words, I have opposite, adjacent, hypotenuse. And if I do this angle here, well, again, tan beta, so beta is 30 degrees, so tan beta is equal to the opposite over the adjacent, which is 1 and root 3. And again, if I get opposite squared plus adjacent squared square root, in other words, hypotenuse squared equals o squared plus a squared, then I get 2. So that's opposite, adjacent, hypotenuse. So what that allows me to do now is to sub in for cos alpha and sine beta here. So cos alpha is adjacent over hypotenuse, which is 2 over root 7. And sine beta, well, sine beta comes from the second triangle here, which is opposite over hypotenuse, which is 1 over 2. So now I have the information that I need to sub in for t here, because it's u times cos alpha, so times 2 over root 7, over g times sine beta, which is 1 over 2. Now, if you actually worked out what alpha was and beta was, it can often end up with a lot of decimal places, which can be a little bit messy. And because Applied Maths is a null course, we tend to have quite nice, neat numbers here. So using our right angle triangles always allows us to keep it nice and neat in surd form. So I'm going to be dividing by a fraction here, so I'm going to turn it upside down and multiply. So I have u times 2 root 7 over g, and if I turn that fraction half upside down and multiply, I end up with times 2 over 1, which gives me then 4u over root 7g. Again, if you did it in decimal form, you could end up with t is equal to 0.51 u over g. So both answers are fully acceptable. So what you're going to do for me now is the 2 exam questions, 2009 and 2004, and I will attach those 2 questions to Edmodo.